Hello, my dear students. Today we shall interact about a doubly reinforced beam which we have understood in the last class. Anyhow, a quick review what is a doubly reinforced beam and when do you provide, and we'll have a review of the derivation what was done. So hence we have defined in the last class the RCC beam in which the steel reinforcement is placed in the tension as well as in the compression zone are called as a doubly reinforced beam. What is the necessity of a doubly reinforced beam? Let us try to understand here. Whenever the depth of the beam is restricted due to constraint like availability of the headroom, architectural or space consideration, and the moment of resistance of a single reinforced beam is less than the external moment. The second, why it is required. When the external loads may occur on either face of a member, the loads are alternating or reversing and may cause tension on both the faces of the member. And also whenever we put the reinforcement in the compression or tension, it improves the diffraction criteria. So hence we can add up this third point. In a similar way, in the case of a continuous beam, the sections or supports are generally designed as a doubly reinforced section, because at the supports you have a negative bending moment arising, and in the midspan you have a sagging bending moment. So hence we provide to resist the sagging bending moment as well as hogging bending moment. In similar way, you may have an beams which are subject to torsion moment. So hence we provide in compression as well as tension. So hence with this regard, we'll go back to the what are these derivations what we discussed in the last class. So a doubly reinforced section comprises of two parts outlined as singly reinforced section with the restriction of the depth providing the limiting moment of resistance mu limit which is less than the design moment mu. That means to say this beam is subjected to mu limit. And the second part what you are seeing here, based on steel beam theory, a steel beam with tension and compression reinforcement is provided the balance moment given by mu minus of mu limit. So hence you are seeing a pictorial representation of a doubly reinforced beam. So let us try to understand a singly reinforced beam can resist still and mu limit only. So hence for that we are going to design for the balanced steel. So what is balanced steel here? You have compression force Cu and Tu. So hence Cu is equal to T1, then we tell it is a balanced section. But if you have the more than the mu max or the mu limit, then we provide the additional steel in the compression zone, because if when we provide here it becomes an over-reinforced section. So hence we provide in the top layer. But when we provide this becomes an unbalanced section. So hence with this regard we provide to counterbalance this force, we provide additional steel here. So hence that is called HTT2. So hence here to resist mu limit, as I told you, Cu is equal to T1. I have written the equation Cu is equal to T1, and in the first module we have learned the derivation for Cu 0.36 FCK XU into B. In a similar way, T1 is nothing but a force created in the tension steel. So hence stress into area, this is called a characteristic stress, and hence the design stress is equal to the characteristic stress divided by partial safety factor. And we know the partial safety factor for steel is 1.15. So hence F of phi divided by 1.15. And when I take this in the numerator, so I get 0.87. So hence with regard, AST1 is equal to 0.36 FCK XUB by 0.87 F of phi. So hence this is the equation for AST1, and using this XU by D, XU max by D, we get 0.87 F of phi AST1 by 0.36 FCK BD. Now for the extra moment, we had to provide the compression steel here. So hence we have to take the moment. So hence force into the perpendicular distance, that is FSC into A is the force into the perpendicular distance d minus of d dash. So hence I have written here mu max minus mu limit is equal to FSC and ASC to d minus of d dash. But when we talk about this FSC, it is depending upon the type of steel what we provide. So hence in IS 456 page number 70, this is a page number 70, where you see the stress strain curve for a mild steel is equal to F of phi divided by 1.15. So that comes to stress is equal to 0.87 F of phi. But in the case of deformed bar, it goes on changing with each value of strain. So hence the detailed version in the SP16 is given a graph here. Stress versus strain. So hence this is a pictorial representation. What is been told in the IS 456, the similar graph has been shown in a detailed way. So hence it tells for each value of strain, the stress goes on variation. So hence you are supposed to find out the strain, later the stress. So hence to find the strain, what we do, we draw an triangle where it is the maximum strain in the concrete here and the steel in the compression steel ESC. So hence I have two triangles, one triangle and the second triangle. So hence the first triangle is here, second triangle. So hence based on these two similar triangles, we write down a relationship 0.0035 divided by XU max is equal to EXE, and this is XU max minus D dash. So hence with that we get ESC is equal to 0.0035 XU max minus D dash by XU max. So hence a similar formula is given in the code book page number 96. That's what I showed you, mu minus mu limit Fs in AS in d minus of d dash, and to find the strain, this is the equation which is given in the code book. So hence similar formula I have written in the notes here. ESC is equal to 0.0035 XU max minus d dash minus XU max, which is similar, is written in the code book. And now to find out the FSC, we have to go through the SP16 by referring the graph. If in the case of mild steel, it will be FSC is equal to 0.87 F of phi. But in case of 4 and 5 as well as 500, I have to refer the graph. But to refer the graph, it takes time examination. So hence, you have a table number A, page number 6 of SP16, where for F of phi 4 and 5 is being given. For each value of strain what you calculate here, you can find out the stress here. And if it is in the case of F of phi 500, you can find out the strain and find out the stress. So hence if the value is in between, you can do the interpolation. So hence that's the basis of finding out the FSC. So for counterbalancing the steel provided in the compression zone, we tell CS is equal to T2. So hence CS is equal to T2 here. FSC and ASC is the CS is equal to T2 F5 by gamma M and AST T2. So hence gamma M is nothing but 1.15. If it's go to the numerator, I will get as 0.87 F of phi AST T2. So hence AST T2 is equal to FSC ASC by 0.87 F of phi. So hence the total steel provided in the tension zone is nothing but AST1 plus AST T2. AST1 we have calculated by using this equation, and AST2 is being derived just now here. The same equation is given here for AST2 is equal to ASC FSC by 0.87 F of Y. So hence same formula I written here. So hence the total steel is equal to AST1 plus AST2. So this is what we do for the fracture. AST1 we find out, AST2 we find out, as well as ASC we find out. So hence with this basics which was learned in the last class, we'll go into a numerical problem. I hope in the last class we have done 2 problems in complete manner, and hence now we'll discuss about the problem number 3. Here a doubly reinforced concrete beam 250 by 450 mm. This is a keyword we observed in the problem. It is called effective depth is given. Is required to support 40 kN per meter, including the self weight, effective span is 5 meters, effective cover is 50 mm, using M20 concrete, Fe4 and 5 steel. Find the steel for flexure and shape. A similar kind of problem can be given also, like the change in the grammar, that is a design a reinforced concrete beam of rectangular cross section using the following data. Effective span 5 meters. Yes, this problem also 5 meters, this problem also 5 meters. Width of the beam is 250 mm. Overall depth is 500 mm. Observe the keyword here. Service load including the dead load and the live load is equal to 40 kN per meter. Here this problem is not given. Whenever it is not given, please take that as an service load only or the working load. Including the dead load and live load 40 kN per meter. Young's modulus is given in this problem. Effective cover is given. Similar way, adopt M20 grade concrete and Fe4 and 5 grade steel. Sketch the reinforcement details. And additional data may be given if it is given for 16 marks. Check for the beam depth for control of diffraction using empirical method. So hence, first we shall interact about the beam should be designed for beam movement as well as shear force. So the first question is given design doubly reinforced beam. The second problem, nothing is given, but whenever breadth is given in the problem and the overall depth is given in the problem, that means to say it is an doubly reinforced section 99%. So both the problem are of same kind. Only the special in this problem is Young's modulus of steel is being given here. So hence, based on this, the first step, the problem will write down the data given in the problem, that is the breadth of beam is given as 250. The effective depth is given as 450 mm, and here in the second problem, the overall depth is 500 and effective cover is 50. So hence 500 minus 50 is nothing but 450 mm, and d dash is 50 and the overall depth is 500. Now, as I told you in the examination, it can be given like a service load or a working load or a characteristic load or an unfactored load, or nothing can be given, simply a load will be given. Then you are supposed to multiply by the partial safety factor. If in some problems they give ultimate, factor, limit and design load, do not multiply by partial safety factor. So hence always the design load is equal to the characteristic load multiplied by the I'll show you the formula which we discuss in the limit state design, that is given in the limit state design, like page number 68. This is what the design load is given by the characteristic load multiplied by the partial safety factor. So hence here This load is given as an service load, hence you have to multiply 40 into 1.5. So hence you will get 60 kilonewton per meter. And the grade of concrete is given as FCK 20 Newton per m square, F of 5 is 405, and XU max by D is equal to 0.45, which has been given in the page number 70 of the code book, which we did the derivation. Observe here, a 4 and 5 is 0.48. So hence with this data, we'll go ahead with the calculation of maximum moment and shear force. As we know that this problem is subjected to a uniform distributed load, M is equal to WL squared by 8. And similarly, the maximum shear force at the support, the total load is W for a span of L. So as you have two supports, this will be WL by 2. So hence WL by 2 you will get as 150 kilonewton here, as well as the bending moment you will get 187.5. So hence, based on this, we would go with the check for the type of the beam to check with the MU limit in the equation. So hence, the page number 96 of the code book, for a balance section, we have equation as MU limit is equal to 0.36 XU max by D 1 minus of 0.4 to XU max by D BD square FCK. So hence, I apply the same equation here what has been given in the code book. So substitute the values of grade of concrete, XU max by D 250, 450 square into 1 minus of 0.42 into 0.48. So hence, you would get the bending moment is 139.68 into 10 power 6. So hence, convert into kilonewton meter. So hence, divide by 10 to the power of 3 for Newton to kilonewton, mm to meter, divide by 10 to the power of 3. So hence, the total will be divided by 10 to the power of 6. Hence, 10 to the power of 6, 10 to the power of 6 gets cancelled. So hence, you would get as 139.68 kilonewton meter. Whereas, the MU limit here is problem MU is equal to 187.5. But this beam with this breadth, with this depth, with this maximum value of XU max by D, it can resist only 139. So hence, the as in 139, 187, if you want to resist 187 and you want to design single reinforced beam, the only chance is to increase the depth of this. But unfortunately, the problem already the depth of the beam is given here. So hence, I don't have a freedom to change the depth as well as the grade of concrete as well as the grade of steel. So hence, with regard, we come to a conclusion that MU limit is less than MU max. Hence, design it as an doubly reinforced section. So hence, with this, we have came to a conclusion that we'll go ahead with the doubly reinforced section. So hence, you have to resist the MU limit, and for the extra moment, MU max minus of MU limit. So hence, for the MU limit, I hope we did the formula, that is using XU by D is equal to XU max by D, the simple formula which we discussed just now with the derivation that is given in the notes. So hence, this was the derivation XU by D, XU max by D is equal to 0.87 F of EST1 by 0.36 FCK by D. So that's what I've written here, the same formula. Substitute all the values of grade of concrete, grade of steel, as well as the breadth and the depth. So hence, you will get as 1076.85 mm squared. And later, for resisting the extra moment, you have an equation MU max minus MU limit is equal to FSC to ASC D minus D dash. By chance, you forget the equation that is there in page 96. MU minus MU limit is equal to FSC into ASC D minus of D dash. So hence, with that equation, substitute here in the equation here, But we have to first find out the value of FSC. So hence, in this problem, something called Young's modulus of steel is given as 2 into 10 raised to 5 Newton per mm square. So hence, if I find out the strain, then I know the ESE. So hence, we know that stress is equal to force by area. So hence, that concept I can find out, or Young's modulus is equal to stress by strain. So hence, I will write in the equation stress is equal to strain into Young's modulus. So hence, what is the strain? Already I told you in page 96, you have the formula 0.0035 axial max by d dash by axial max. So hence, I substituted here the value of axial max as 216, which we have calculated the first step only. Axial max by d 0.48. Axial max is equal to 0.48 into 450, 216 mm. That's what I am going to substitute it here. 216 minus 50 by 216, 2 into 10 raised to 5. So hence, I will get as 537.96. So that I rounded for 538. In similar way, we have from the codebook SP16 for FR5, 4 and 5 for the actual value of strain, what is stress? So hence, let us calculate the actual stress. So hence, strain is calculated in the similar way what has been substituted the value of axial max. So hence, you get as 0.00268. And now, referring the table number A, page number 6 of SP16, you have these values of strain and stress. So hence the same values I will written here 0.00241. For 0.0241 you have 342.8, and for 0.00276 you have 351.8. That's what I've written here. So now for actual value of 0.0027, what will be the value? So hence, do by interpolation, so hence you will get Fs is equal to 350.25 Newton per m square. Hence, the value of FSC both are in that range only, hence the value is correct. So hence, now substitute the value of FSC here in this equation, which we have written here. There is mu max on mu limit, Fs in ASC d minus d dash. Substitute the value of FSC, so hence you get AS is 341.24 mm square. So hence with this, I gave guidelines that if the area of steel is from 0 to 500, take 12 mm, 500 to 1000, take 16 mm, 1000 to 2000, take it as 20, 2000 to 2000, 3000, take 25, and if it's more than 3000, take 32 mm square. So hence with this idea, assume 12 mm now and find out the number of bars. So that's what the procedure has been done here. So you can find out that is 341.24 divided by pi into 12 square by 4. We'll get 2.99. So hence it is rounded to 3 bars of 12. And similarly, we find out the ASTT2, ESC, FSC by 0.87 FR5. Hence, ESC are provided as 3 bars of 12. So hence I substitute the value here. FSC is substituted 0.87, 4 and 5. We will get as 329.14. Now add up. EST is equal to EST1 plus ASTT2. So hence you will get as 1405.99. And now as the range is from 1000 to 2000, assume 20 mm and find the number of bars. That's what we did. The beam designed for bending moment, and we designed a doubly reinforced beam. Now finally, this beam should be verified for the shear reinforcement. We know the shear force in this problem is Vu is equal to WL by 2. So hence you got 150 kilonewton. So hence we go with the procedure which is given in the code book, page number 72. So you have a procedure here. So first we are going to find out, this is a word, the keyword, limit state of collapse for the shear. So tau V, stress caused due to shear force, VU by BD. So hence I have done the similar formula, shear force divided by the cross-sectional area 250 into 450, we get as 1.33 Newton per mm square. And later we have to work out what is the calculation of tau C based on the percentage of steel and the grade of concrete. So hence we are going to refer page number 73, table number 19, where the percentage of steel is given here as 100 AST by BD and with respect to grade of concrete. So hence first we calculate what we have provided. 5 bars was provided as steel, 5 into pi into 20 square by 4. So hence we get 250 into 450. Hence with that regard get 1.39. So hence 100 AST by BD M20. So hence we are going to refer this code book for a value of 1.25. 1.25 is somewhere here and 1.5 there. So for 1.25 for a grade of concrete is 0.67 and for 1.5 have 0.72. So hence with the regard I have written here. So doing by interpolation would get as 0.698 with the values between these two, hence the interpolation is correct. Now here as tau V is greater than tau C, when tau V exceeds tau C, we have to provide the shear reinforcement. Fancy of vertical stirrup we go. You can go with bent bars, but the execution is little difficult. So hence we avoid this. We go with the vertical stirrups. So hence for the vertical stirrups, it is told here how do you find out that. This is what vertical stirrup. First we have to find out what is the shear reinforcement shall we carry to carry a shear force equal to VU minus of tau CBD, and that is called as VUS in the problem. So hence I have done the step VUX is equal to VU max minus tau CBD, which has been told just now. To find this, VUS is equal to VU minus of tau CBD. So hence I substituted the VU max, I substituted the tau C, B into D 450, hence I will get as 71.85 10 cube Newton. And later we find out, once we get VUS, we apply this formula for vertical stirrup. VUS is equal to 0.87 F of ESVD by SV. Now ESV always we assume as 2 leg 8 mm stirrup, so that comes to 100.53 mm square. So hence the unknowns are VUS is known to you, 0.87 F of is known to you, ASV is known, what is the ASV is unknown in this problem. So hence find out the SV. So this is what ASCB, you have calculated 2 into pi into 8 square by 4, 100.53 mm square. So hence we got as SV is equal to 227.37. But the code book, when you refer page number 47 of the IS 456, it tells that you have the maximum spacing should not be greater than 0.75 times of D or not greater than 300 mm. So hence page number 47 up to the guidelines. The maximum reinforcement of shear reinforcement shall not exceed 300 mm or 0.75 times of D. That's what I've done here, 0.75 times of D or 300 mm. So hence we will provide 2 leg 8 or 225 center to center. So hence the check for bending moment and check for shear reinforcement is over, but there is a small step given in the problem, check for deflection control. How do I check the deflection control? We have L by D actual. the span of this problem given in the question is given as 5,000 and the effective depth is given 450. Hence, you would get as 11.11 in this problem. And similar way, the L by D maximum is equal to L by D basic into the tension modification factor for tension enforcement, modification factor for compression enforcement, modification factor for a flange beam. And anyhow, the flange beam is not here, so hence only KT and KC comes into picture. Now, how do I calculate KT and KC is a step. So hence, when you refer page number 33 of the code book, you have a graph given there. I shall show you the graph, and which we already understood in the case of a singly reinforced section. Now, the L by D basic for a simply supported is given as 20. That's what I've written here. L by D is 20 in this problem, and it depends upon the modification factor depending on the area of tension in the tension enforcement. I refer figure number 4. So hence you have a figure number 4 where this is a chart what we're going to refer to find out that. In a similar way, in the code book is told that if I provide a compression enforcement, so refer figure number 5. That's what will be told, figure number 5 to be referred. So hence, with this regard, we'll try to understand how KT is found out. So what is KT depends upon the percentage of reinforcement here and modifying factor, so I can do the interpolation and then find out. But Fs is given as in the code book, page number 38.58, F of phi, area of the cross section of the steel required divided by area of the cross section of the steel provided. So hence here I worked out the area of the steel by the B into T 1.39 and percentage of tension reinforcement I got 1.39, percentage of compression reinforcement I got 0.3, and referring to the figure 4 which I explained here using the equation I have calculated here what is the value of FSC. You got as 215.45 Newton per meter square. Now with this, what we do, we know the value of percentage of tension enforcement here is 1.39, that a round off of 1.4, Fs is 215. So hence what we do here, refer the chart for 1.4. So 1.4 is 1.2, 1.6, 1.4 is somewhere, come over here, and then you have the value of the stress is 215. So hence you refer here is between 190 and 240, 215. So hence when I go with this for 0.8, I'll get the modification factor as 1. That's what written here. Modification factor is KT is 1. In similar way, to find out the KC, we refer this chart where we have a percentage of compression enforcement. We found out the percentage of compression enforcement in this problem is 0.30. So hence for 0.30, 0.25, 0.5. So 0.30 may be here, then come over here. So hence KC is equal to 1.1. So hence I written here as 1.1 for KC is equal to 1.1. So hence L by D maximum is equal to L by D basic. So hence page number 37 tells that for a simply supported beam it is 20. So hence I substitute 20 into 1 KT into KC 1.1. So hence 22. So hence L by D actual is 11.11 in this problem, and comparing to this L by D maximum is 22. So hence it is safe against deflection. So hence we have designed for bending moment, we have designed for shear force, and we checked whether it is safe against deflection based on the percentage of reinforcement given in the tension zone as well as in the compression zone. With this criteria, we go with the abstract of the design. That bottom is going to provide 5 of 20 bars tension zone. The compression is 3 of 12, and this is what the stirrups what we design is 2 leg 8 or 225 center to center, and write down the specification of the kind of material what we're trying to use, M20 and 4 and 5. As you written as 250 and 500, so hence we have to, as a structural engineer, I will tell what is the dimensioning here. So hence, as an engineer, you tell all dimensions on mm. So this completes your problem here.